all of you. Is everything all right? Can you start our session? So today we will be discussing photoelectric and Compton effect. Can you start? I hope everything is all right. So these two topics are very familiar to you, although for the sake of completeness we have to do this. Not a difficult topic, let's say photoelectric effect. So let's quickly go through this, the photoelectric effect. So it gives you the direct evidence of the particle nature of radiation. Good morning, Murli. Okay, so let us see. It gives you a direct confirmation of the energy quantization of light. Okay, this effect involves the emission of electrons from when electromagnetic radiation such as light hits a material. As you can see, we have some metal which contains electrons. Now when you shine electromagnetic wave or light on it, and if the energy of the light is more than the work function of the metal, electron will be ejected. Okay, the photoelectric effect requires photon with energy from a few electron volts to over 1 MeV. So this is very important. How much energy falls under this effect of photoelectric effect? It may be few electron volt to 1 mega electron volt in high atomic number elements. And this study of the photoelectric effect led to the important steps in understanding the quantum nature of light. Light carries the quanta, photon. Electrons and influence on the formation of the concept of wave particle duality. So this gives you an experimental basis of the wave particle duality theory. So it also led to Max Planck's discovery of the quantized energy and the Planck relation E equals to h nu, which links photons frequency with its energy. Now few things we need to know about the photoelectric effect. This is precisely the photoelectric effect. Photon comes, electrons overcome the surface potential and ejected. So you are sending wave, and what you are getting? You are getting particle. So wave in a way interacting with particles. So we can say that this wave has some materialistic or particle like behavior. Now this is precisely the photoelectric effect. Now if the frequency of the incident radiation is smaller than the metal's threshold frequency, we can say, let's say this is nu 0, a frequency that depends on the properties of the metal. If you multiply, let's say, this threshold frequency nu 0 with h, so this becomes the unit of energy, right? So this energy is known as the work function. So if the incident radiation's energy is less than this, no electron will be emitted regardless of the radiation's intensity. Remember two things here. One is energy, another one is intensity. Energy mainly depends on the frequency. Okay, you need to give some energy which is more than this energy h nu 0, and radiation intensity means how many photons you are sending. Okay, you are sending one photon, the intensity will be less. You are sending two photons, intensity will be more. If you are sending more and more number of photons, means you are increasing the radiation intensity. You are not increasing the energy. Energy increasing means increasing this nu value. So remember this one, radiation intensity is not crucial when your incident photon frequency is less than h, this nu 0. So it must be more than nu 0, and then radiation, if you increase the radiation intensity, then the photo current will increase. This is the first point. Second point, no matter how the intensity of the incident radiation, electrons will be ejected instantly the moment frequency of radiation exceeds the threshold frequency. It is not like that you are sending photon, then electron will absorb, then it will emit, and it will take time. It's not like that. It's instant. As soon as you shine the surface of the metal, electron will start coming out. At any frequency above nu 0, this is the threshold frequency, number of electrons ejected increases with the intensity of light. Okay, let's say you have sent 2 photons, and the energy of the photon is above the threshold energy, you can say. Then whatever be the number of electrons, if you are giving, let's say, instead of 2 you are giving, let's say, 10, then obviously this photocurrents the photocurrent will increase, because you are increasing the intensity. Kinetic energy of the ejected electrons depend on the frequency but not on the intensity of the beam. This h nu you are sending, and this is the minimum you require, and the remaining h nu minus h nu 0, this will be ejected as the kinetic energy of the photoelectron. And we will see that kinetic energy of the ejected electron increases linearly with the incident frequency. Okay, so these are some basic things we need to know about photoelectric effect. Now let me give you a clearer picture. Let's say this is the metal surface. So let us try to understand the difference between intensity and energy incident. So this is your metal surface. So it contains electrons, somewhat like this. These are electrons. Light is incident, and the electron is getting ejected. Now if you consider one photon, then it will be h nu, and if you say there are n number of photons, then the energy will be nh nu. Okay, so this is given by Planck's quantization formula. Planck's quantization formula. According to Planck's quantization formula, the energy carried by the photon is discrete, so n h nu. Okay, and we will take the integer value. N is the number of particles. Now what is the intensity? If I talk about intensity, what is the intensity of the light incident on the metal surface? Intensity I is energy per unit area per unit time. So what is the energy? If there are n number of photons or particles, we will have n h nu divided by A times T. So energy, this n h nu is the energy and this T is the time. So it is power per unit area. So intensity is nothing but energy, power per unit area. Now h nu is incident, and let's say the threshold frequency is nu 0. So the energy corresponding to it will be h nu 0, and let's say we are denoting the kinetic energy by Ek. Ek is the kinetic energy of the electron. So the total is h nu. A portion of it, let's say h nu 0, this is used in overcoming the barrier potential, and the remaining is ejected as the kinetic energy of the electron. This h nu 0 is identified as the work function of the metal surface. This is phi. So we can say that energy, kinetic energy is h nu minus phi, where this phi is the work function of the metal. What is work function? Work function is the amount of energy required to remove an electron from the metal surface. Okay. Look, why no electron is ejected if the incident frequency is less than the threshold frequency. From this we can also write Ek is equals to h times nu minus nu 0, and this is half, if the, let's say the mass of the electron is m, so this becomes half m, let's say V max, this is the maximum velocity with which the electron will be ejected, half m V max square. Now if let's say nu is less than nu naught, if nu is less than nu naught, so this quantity will be negative, so it means Ek will be less than 0. So kinetic energy cannot be negative. If Ek is negative, means V will be imaginary. That means no ejection of electron. No ejection of electrons. Another thing we would like to include here, above the threshold frequency, number of electrons, photoelectrons actually, number of photoelectrons is proportional to number of incident photons. Now if we plot this thing, I don't have a space here, but let us try to plot. Let's say we are plotting kinetic energy, just a moment. If we are plotting, let's say, kinetic energy versus intensity, so what kind of graph we can expect? Kinetic energy versus intensity. Let's say nu is fixed, then you will get a straight line. What does it show? It shows nu is equals to constant. No matter how many particles you send of a particular energy, kinetic energy will not change. Okay, because kinetic energy depends only on the incident energy, not on the number of incident photons, because that is why it is giving you a straight line like this. On the other hand, if I plot, let's say, kinetic energy versus the frequency, kinetic energy versus frequency. So kinetic energy versus frequency will be dealt with this equation. You can see this equation, right? So you can see it is y is equals to mx plus c formula with the slope. You see slope is positive, but this intercept on the y-axis is negative. How much is the intercept on the y-axis? It is minus h nu 0. So let's say this is minus h nu 0, this portion is minus h nu 0. So your straight line will go somewhat like this. In the positive side, it will go like this, and it will cut here, somewhat here. What will be this value? This value will be h nu 0, and where it will cut nu is equals to nu 0, because you see, if you put nu equals to nu 0, this value will be 0, kinetic energy will be 0, and that is 0. So Ek versus nu gives you a curve like this. Is it clear, guys? Tell me, or is there any question? Now, what was the experimental setup for this particular experiment? The experimental setup looks like this. You see, the experimental setup for studying this photoelectric effect is shown in this figure below. So it is consisting of some evacuated gas tube. So you can see this one. I will share this PDF in the course folder. You just go through it once, because in future question may be set, and for that you need to have the understanding of the experimental setup. So we have an evacuated glass tube having two electrodes. One is this cathode, another one is this anode. Cathode means it will eject electron. So it is basically the metal surface which we are talking about. The photoemissive electrode C is connected to the negative terminal. Okay, negative terminal, and it is known as photocathode. The electrode A, this acts as an anode, and it is connected via some rheostat, and it is connected to the positive potential. Rheostat helps to maintain a desired potential between the cathode and the anode. So electrons will get ejected from the cathode, and the ejected electron will get attracted towards the anode with the application of this potential difference. And motion of electron means current, which is known as photocurrent, and the electrons are known as photoelectrons. So these photoelectrons get attracted towards the positive potential of the anode, resulting in the generation of the photoelectric current in the circuit. Now, to measure the voltage, we have added a voltmeter, and to measure the current, a microammeter is connected. So this is precisely the experimental setup. Now, when the incident radiation is false on it, the photoemissive material, electrons will get ejected, electrons will get attracted towards the anode, because this is negative, this is positive, and photoelectrons will be generated, and that will give you photocurrent, and with that help we can measure this photocurrent. So this is precisely the experimental setup. Now some observation, like increasing positive potential of the anode increases the photoelectric current, obviously, reaching a saturation value where all emitted electrons contribute to the current. So more it attracts, more electrons comes, means photo current will increase. Applying a negative or retarded potential decreases the current. This is one thing. You see, this is negative, this is positive. Okay, electrons are itself negative. So negative is getting attracted towards positive, so it is attracted. Now if you apply, let's say, retarded potential, means negative potential on this anode, what will happen? Electrons are negative, you are applying negative potential, so this electron's motion will be retarded, and there will be a time when this negative potential will momentarily stop this motion of the photoelectrons. So that particular potential or retarding potential is known as the stopping potential. Stopping potential is denoted by V0. So once this negative potential V0 is reached, electrons motion will be hampered and there will be no current. The current drops to 0 as even the fastest electron fail to reach the anode. So when the potential in the circuit is equal to the stopping potential, there is no current in the circuit. And how can we relate the stopping potential with the maximum kinetic energy of the photoelectron? So let's say you have applied V0 potential. So what is the energy corresponding to V0? We just need to multiply the charge of an electron. So EV0, this is the energy. This would be equals to the kinetic energy maximum, which is half m Vmax square. And from this we can calculate the value of the maximum velocity of the electron. So this will be square root of twice E V0 divided by m. So sometimes we can expect some question involving the stopping potential and the maximum velocity of the ejected electron. Now there are two graphs which will help you understand this scenario better. So look at these graphs. The first graph, here we are plotting photoelectron versus intensity. So above the threshold frequency, if you increase the intensity of light, means if you are increasing the number of photon incident, the photoelectric current will keep on increasing. Why? Because more number of charge carriers are involved, isn't it? So you see the current, what is current? I is rate of flow of charge, dq by dt. Now what is this dq? If let's say there are n number of charges, and if one charge is carrying the charge of an electron, so it is E times dn by dt. You are increasing the intensity of light, means you are increasing this factor. So that is why this photoelectric current increases linearly. Okay. Now about this photocurrent, you see when you are applying positive potential, means you are giving anode the positive potential. So it will attract this photoelectrons and the electrons will flow and current will be generated. So that is why you can see when positive potential is applied, current is increasing, and momentarily, meanwhile, it achieves the saturation, because when the number of ejected electrons will be saturated, no matter what positive potential you apply, there will be no extra generation of electron. So that is why after some time the photocurrent is getting saturated at fixed frequency and intensity. If you increase frequency, then there may be some increased current, but for a fixed frequency and intensity, it will get saturated no matter what accelerating potential you apply. Now on the other hand, as soon as you start applying the negative potential, means if you make the potential of the anode negative, so this will hinder the motion of the photoelectron, it will repel the photoelectrons. As a result of that, photocurrent will keep on decreasing, and when you apply sufficient negative potential or retarding potential, which is equal to the stopping potential, then there will be no photoelectron left and the photocurrent will become 0. So this is the stopping potential. The potential, applying potential, if it is positive, then we will call them accelerating potential, and if we are applying some negative potential, it will be termed as retarding potential. Okay. So precisely we have covered the theory of photoelectric effect. I hope now you are in a position to tackle any kind of numerical which may be set from this particular topic. So let us try one problem. Then photoelectric effect, the incoming radiation with frequency nu0 with h nu0 is equals to 8 electron volt. Remember this one, nu0, it is the unit of frequency. Once you multiply h, it becomes the unit of energy. Let's say V is potential. If you multiply E, it becomes energy. So these are simple facts. electrons of energy 3 electron volt are emitted from metal surface. So you have, let's say, a metal surface like this. This is the metal surface. What you are doing, incoming radiation of frequency h nu 0. So h nu 0 is given 8 electron volt. Electrons of energy 3 electron volt is emitted. So Ek 3 electron volt. The energy of the electrons emitted from this surface when the radiation frequency is 1.2 nu 0. So when it is 1.2 times h nu 0, so obviously 1.2 into this 8, then what will be the kinetic energy of the electrons? Can you do this? Initially h nu 0 is coming, so h nu 0 this is the total energy you have. So this will be used to overcome the work function of the material, and the remaining energy will be emitted as the kinetic energy of the electron. So it is given 8 electron volt, phi is not known, Ek is 3 electron volt, right? So from this we can get the value of the work function of the metal, that is 8 minus 3 electron volt means 5 electron volt. So 5 electron volt is the work function of the metal. Now if nu is changed to 1.2 nu, so the total energy now becomes h times 1.2 nu 0, right? So for this, what will be the energy of the electrons emitted from the surface? One thing is fixed for this metal, that is the phi value is fixed. So this will be equals to phi plus, let's say, the kinetic energy, new kinetic energy of the emitted electron under this scenario is Ek prime. So we have to find out this Ek prime. So what is this Ek prime? Ek prime is equals to h nu 0 into 1.2. So 1.2 h nu 0 value we know 8 electron volt. Okay, minus 5 electron volt. And this is 9.6 electron volt, 9.6 electron volt minus 5 electron volt, that is 4.6 electron volt. That is precisely matching with option D. Is it clear or not? Tell me. Murli, Hari, whoever is there, is it clear? Can we move forward? So we have done photoelectric effect. Let's move on to Compton effect. This effect is also very important. So let's briefly talk about this Compton effect. In photoelectric effect, what we have done, we have sent photons and the electrons got emitted. Now in Compton effect, what we have, this also gives you the direct evidence of the particle nature of radiation. Compton scattering discovered by Arthur Holly Compton is a scattering of high frequency photon after an interaction with a charged particle, usually an electron. So here a photon will interact with electron. Let's say the electron is kept at rest. So after this interaction, the photon will be scattered and the electron will be recoiled. So this was the original direction. So you see the photon is scattered and this one is recoiled, we can say. Number of emitted electron depends only on the intensity of the incident photon, not energy of the incident photon. Am I correct? So you see, it is like energy of the photon. Energy of the photon, it is the minimum criteria. It is like the entry ticket. Okay? It is like the entry ticket. So if you send one photon, let's say, so electron will be ejected if it is more than, if h nu is more than h nu 0. Okay, electrons will be emitted. Now if it is less than h nu 0, no matter what, how many photons you incident, there will be no emission of electron. Okay, so it is like, let's say, if I talk about the metal surface, the metal surface has work function, let's say 5 electron volt. Okay, now you are sending some photon which has energy 4.9 electron volt, and let's say there are 1000 photons. 1000 photons are there, and but the energy is 4.9 electron volt. Then there will be no emission of electron, no electron. Okay, and let's say instead of 1000 photons, you are just sending 2 or 3 photons of energy 5.1 electron volt. If you incident that, there will be ejection of electron. Okay, now instead of 2-3 photons, if you use, let's say, 10 photon, the number of electrons will be more. If you give 100, more photoelectron will be ejected. And in this scenario, 4.9 electron volt, if you send 1 lakh photons, let's say 1 lakh photons of energy 4.9 electron volt, there will be no electron. I think you got the point now. Number of electrons depends on the intensity of the incident photon. When the energy of the incident photon is more than the work function, or the frequency, incident frequency is more than this threshold frequency. Yes. Let's go for this Compton effect. So you see, you send a photon and it will experience the scattering. So obviously this will release energy, this will lose some energy, so its frequency will be changed, let's say h nu prime, and obviously this h nu prime will be less than the original energy. Okay, because this electron was at rest initially and it is getting scattered at some direction, so it is gaining that energy which is being lost by this photon. So it results in decrease in energy. Decrease in energy means what? If it is, let's say, the corresponding wavelength is lambda here and the corresponding wavelength is lambda prime. Decrease in energy means increase in wavelength. They are reciprocal. So lambda prime will be more than lambda, but this nu prime will be less than nu. So this is a precisely simple thing. So this effect is known as Compton effect. Part of the energy of the photon is transferred to the recoiling electron. The electron which is scattered in this way is called recoil electron. Inverse Compton scattering occurs when a charged particle transfers part of its energy to a photon. Now, let us try to visualize this incident. So, scattering of X-ray photons can be treated as the collision of a photon of initial momentum h by lambda 1. So, let us say momentum lambda is equals to h by p. This is a de Broglie relation. We will talk about it later, but for the time being, I think you already know. Okay. So, momentum becomes h by lambda. So, you are sending, let us say, initial momentum p1, and there is a free electron. Using conservation of momentum energy, momentum of the scattered photon means this one. So, we can consider it to be p2. P2 will be h by lambda 2, p1 will be h by lambda 1. Let us see if we consider lambda 1 or lambda prime, whatever suitable thing you have. Okay, lambda 1, lambda 2 or lambda prime, whatever you want to apply. So, for here in this derivation we will be using lambda 1 and lambda 2. So, let us talk about that, lambda 1 and lambda 2. So, the change in wavelength of the photon is given by delta lambda is equals to lambda 2 minus lambda 1 h by m naught c into 1 minus cos theta. So, this expression is very important. What is the Compton shift? Delta lambda h by m naught c into 1 minus cos theta. So, sometimes you are asked to calculate. M naught is the mass of the electron. And if the Compton effect is done by some other particle, then the mass of that particle will be given here. So, this equation is known as the Compton equation. Okay. So, let us try to derive it. Simple derivation we have of this Compton equation. So, you can see in this picture we have some electron which was at rest. We have sent some incident photon and the electron gets recoiled and the photon gets scattered in this way. So, let us say let lambda 1 and lambda 2 be the wavelengths of the incident and scattered X-ray photons respectively. For incident it is lambda 1, for scattered it is lambda 2, you can see here. So, the corresponding momentum will be h by lambda 1 and h by lambda 2. So, P1, P is what? For a photon, energy is given by E is equals to Pc. So, P is equals to E by C. So, here is E1 by C. So, this is h by lambda 1. And what about P2? P2 is E2 by C, that is h by lambda 2. Now, we have to apply conservation of energy and momentum. You see, the photon was supposed to visit in this original direction. This was its original direction, but it is going in this direction instead. So, this angle, this deviation from this original direction is known as the scattering, and the corresponding angle is the scattering angle. So, we can use conservation of momentum here. So, applying conservation of momentum, we get, what does the conservation of momentum say? Momentum says, it says that the momentum before the scattering and after the scattering will remain same. What is the momentum? So, electron was at rest initially, so the momentum was coming from this. So, if I write in a vector form. P1 is the momentum, initial momentum. What is the final momentum? Let's say the momentum here is P2 and here it is the momentum of the electron. This is the recoil electron. Momentum of the recoil electron is denoted by Pe. So this is nothing but P2 plus Pe. Okay. So using the standard vector algebra, we can write Pe. Okay, let's reshuffle this. P1 minus P2, and using the vector law of addition, Pe square is equals to P1 square plus P2 square minus 2 times P1 dot P2. What does it mean? P1 square plus P2 square minus 2 P1 P2 cos theta. So this value of P square will be utilizing later in the upcoming derivation, in the upcoming calculation, let us say. So this value we are saving it for the time being. Pe, this is the momentum of the recoil electron. Other thing needs to be specified, what is theta and what is phi. Theta will be termed as the scattering angle and phi is the recoil angle. This is scattering angle or angle of scattering angle theta, and as it is showing the recoil electron, it is known as recoil angle. Okay. Now if we say that the electron was at rest, so for an electron of mass m0 which is at rest, what will be its energy? Its energy will be E0 equals to m0 c square, right? This is your electron. Now we can apply the conservation of energy. Applying conservation of energy, we get energy conservation also says that energy before, total energy before scattering will be equals to total energy after scattering. Look, initially the electron was at rest, so the momentum was 0 for electron, only momentum contribution was from the photon. Now when you consider energy, although it is at rest, it will have rest mass energy, right? So what is the energy for the photon? It is P1 C equals to PC formula. Then we have to add the rest mass energy of the electron. This will be equals to the total energy of the recoil electron plus the scattered photon. So what is the energy of the scattered photon? It is P2C. And what about the energy of this recoil electron? You know, we can use the relativistic expression of energy. E square is equals to m0 c square into p square c square. Okay. So what is the energy of the recoil electron? It is rest mass energy m0 square c to the power 4, actually E0 square plus Pe square c square square root. The original formula I think you know. I'm just writing the original formula here. Original formula is E square is equals to E square is equals to P square c square plus m0 square c to the power 4. Okay. This is the relativistic energy, expression of energy. So we have used this. What is E? Square root of P square C square plus this is mc square whole square. So mc square is the rest mass energy E naught. So that is why we have written E naught square. I hope this is clear. Now carefully look at this. This is E naught plus P1 minus P2 into C. This is equals to square root of E naught square plus P square C square. Now squaring both sides. Squaring both sides. I am doing every step so that you understand it better. Both sides we get E naught square plus C square, or better we write P1 minus P2 whole square C square plus 2 E naught C times P1 minus P2. This is equals to E naught square plus P square C square. Okay. So this E naught square can be cancelled from both sides, and if I divide by C square, we can write PE square equals to the C square get cancelled. So what we have, P1 minus P2 whole square. So it is P1 minus P2 whole square plus 2 E naught. C by C square is C, so 2 E naught by C times P1 minus P2. Clear? Now let's plug in the value of PE square from this equation. Okay, which is P1 square plus P2 square minus 2 P1 P2 cos theta. So P1 square plus P2 square minus 2 P1 P2 cos theta, and this one is P1 square plus P2 square minus 2 P1 P2, and this 2 E naught by C P1 minus P2. So we can write here putting the value of P square. So you can easily see P1 square and P2 square is getting cancelled from both sides. So what you are left with? You are left with, therefore, P1 P2 into 1 minus cos theta. This 2 is also getting cancelled with this 2. So we have E naught times P1 minus P2 divided by C. I think everything is going smoothly till now. Now you see, if you this multiply, if you divide this P1 by P1 P2 on both sides, what you get? So this is 1 upon P2 minus 1 upon P1. Okay, and let's take this on this other side. So C by E naught into 1 minus cos theta. Now we know that lambda is equals to H by P. So 1 by P is nothing but lambda by H. So 1 by P2, we can say lambda 2 by H, 1 by P1, lambda 1 by H, and this by H is taken to this numerator, so HC by E naught into 1 minus cos theta. Or lambda 2 minus lambda 1 is equals to hc, and what is E naught? E naught we have already told you, it is rest mass energy of the electron. So this C and this C is getting cancelled. So we get ultimately delta lambda, that is lambda 2 minus lambda 1 h by m naught c into 1 minus cos theta. This is what we are looking for. This is the Compton equation. This is known as the Compton's equation. If you have any question, you can ask. Just a moment. Is a scattered electron called recoil electron? Yes, the scattered electron is known as the recoil electron. We have written the scattered electron is the recoil electron. So this delta lambda is known as the Compton shift. Okay, Compton shift, and this h by m naught c, this term only known as the Compton wavelength. So when theta is equals to 0, so delta lambda, it may vary if you consider theta is equals to 0. For theta is equals to 0 degree, we get delta lambda is equals to how much? 0. And for theta is equals to, let's say 180 degree, delta lambda will be 2 times h by m naught c. So this delta lambda varies between these two values. This theta is equals to 0 degree. What does it mean? This is known as grazing collision. This is known as grazing collision. And 180 degree, means you are sending photon and it is turning back. This is known as head-on collision. I hope this is understood. Let's do this problem. A photon of wavelength lambda equals to 4 angstrom is scattered from a electron at rest. If the scattering angle is 150 degree, what will be the wavelength lambda prime of the scattered photon? Can you do this problem? To solve this problem, you can use the Compton-Effects formula. Compton-Effects formula you can use here. Delta lambda. Which one is greater, lambda or lambda prime? Obviously lambda prime is greater. So lambda prime minus lambda. This one we have derived h by m naught c times 1 minus cos theta. Okay. Now what is given? Given theta is equals to 150 degree. So we do not know the value of 150 degree. So we need to calculate 1 minus cos 150 degree. Right. So 150 degree can be written as 150 degree means it is lying in a second quadrant. So 180 minus 30. So minus plus cos 30. You know the value of cos 30, that is square root of 3 by 2. So 1 plus root 3 by 2. So precisely approximately this is 1 and this value root 3 by 2 is 0.866. So 1.866. So sometimes if you I think you will be given calculator because you will be giving in online exam. But even if calculators are not allowed, you can easily get the value. So what is the value of delta lambda? Delta lambda is equals to h by m naught c. So h is 6.626 10 to the power minus 34 by m naught. Here it is electron. So what is the rest mass of rest mass? It is 9.11 10 to the power minus 31, and the speed of light 3 into 10 to the power 8 meter per second. And what is left? 1 minus cos theta we have calculated separately, that is 1.866. So if you put all together all these values, you will end up getting 0.045 angstrom. So if delta lambda is 0.045 angstrom, so what is lambda prime? Lambda prime is equals to lambda plus delta lambda. Lambda is 4.000 angstrom plus delta lambda 0.045 angstrom. So this makes 4.045 angstrom. That precisely matches with option 2. Got it? So we have covered photoelectric effect and Compton effect today, and yesterday we covered blackbody radiation. So we are stopping here today, and in the next class we will be dealing with wave particle duality, uncertainty principle, and after that we can start mathematical tools in quantum mechanics. So we are going in a very detailed way, so don't worry, and we will be practicing a lot of problems based on this. Okay, if there is any question you can ask, otherwise let's end the session here. Thank you. Thank you very much, guys.